Okay, let's create one of these non-additivity plots. First thing, real quick spreadsheet technique. If you click on a column header and drag across, then you can click and drag any of the lines in between columns and either compact or expand all the columns at once. That can be a lifesaver if you want to look at a lot of data at once and not like keep scrolling back and forth. Now we're going to create these comparison values. The formula itself is really just the two effects multiplied by each other and divided by the grand mean. It's fairly straightforward, and we can copy those down. They should be different for every data point in this particular model because we only have one data point for each combination of the two factors. Okay. So we want to create a scatter plot now, but we want comparisons to be in the x value and residuals to be in the y. A couple different ways I could do that. I'm just going to right-click, insert a column here, and then click on this column. If I click right until I get those crosshairs, I can swap them out there. This will make my life easier when I go to insert my scatter plot. It'll put everything on the correct axes. And probably would not be a bad idea. Click the plus sign here, add some axis titles, just to clarify that these are the comparison values, whereas these are the residuals. Okay, let's make that a little more visually appealing here. Okay, so now the next question is, do these points fall in a straight line? That is a judgment call, but I mean they seem reasonably. Let's get a little more objective evidence. I clicked on one, right-click, and add a trend line. In that menu, I have the option of displaying an equation and an r-squared value, so I'm going to do that and bring them up here. So notice my r-squared is decent, I guess. 41% of the variance in the residuals can be predicted or explained by the comparison values. So it is a decision call here. If these aren't falling along a line, then we're saying that there isn't an additive model that will work for this data set. If they do fall along the line, it's telling us there is an additive model. We just need to transform our values here, our iron values. So let's say that it's roughly along a line. Then we need to look at this slope here, 0.7236, and to get the actual power of the transformation that we're going to be raising all our y values to, we would take 1 minus this, 1 minus 0.72, so that would give us something like maybe 0.27-ish, 0.28 maybe. So just to go ahead and do that, I'm going to insert, and we'll take this data point raised to the 0.28 power, and we can copy all those down. This would be iron Fe, we'll get a little chemistry fancy here, to the 0.28 power. Now, in reality, you'd probably round it to the next more common, and 0 here. If we would have ended up with a 0, that would have told us to take the log. So another thing we could do is just take the log of each of these values, and that would probably be a cleaner model, even though what the message we were getting from our non-additivity plot was that it might be a little bit stronger than a log, or a little bit higher of a power than a log. Okay, so that's the transformation. Then you could rerun the ANOVA. We're not going to. You could rerun the ANOVA on these values, or on these if you went with the log, rather than the original iron values. And then as you're interpreting various things afterwards, not in the ANOVA chart itself, but if you were doing more specific predictions, you'd have to account for whatever transformation you put the data through.